Okay, in this chapter, chapter number 6, we will talk about ions and the transfer of electrons. Now, atoms can form positively charged ions when they lose electrons, and they become more negative when they gain electrons. Now, at first that may seem counterintuitive. You would normally think that if you gain something, that's good, or if you lose something, that's bad. But think of what is being gained or lost. Electrons have a negative charge. So if you get more of those, if you gain more of those, you are becoming more negative. If you lose electrons, if you lose something negative, that's a good thing. That's a positive thing. So it's very common to get that backwards. A type of bond called an ionic bond is formed when a strong attractive force between a positive ion and a negative ion meet. And see the learning goals of chapter number 6, being able to write the symbols for simple ions of the representative elements. An easy way to tell if an element is an ion or not, a positive or negative charge written just above the chemical's element symbol. Right now, we'll talk about ionic and covalent bonds. Now, chemical bonds are formed when atoms will either lose electrons or gain electrons or actually share electrons to form a more stable outermost shell. The rule is called the octet rule. If you remember nothing else from this chapter, know what this rule means, the octet rule. That is what all elements are striving for. That's when they're the most stable. It's also called the rule of 8. So some atoms or some elements are going to be more likely to lose an electron, so they become more stable, or some elements are more likely to gain electrons, so they become more stable. It just depends what their characteristic is. Two different types of bonds, ionic and covalent. Ionic are formed when electrons are transferred from one atom of nonmetal to another. So basically, one element is stealing away an electron from the other, and by doing so you are forming two separate ions, because one element has lost an electron, forming a positively charged ion. One element has gained an electron, making it more negative. And the stronger type of bond, covalent bonds, these are when nonmetal atoms are sharing equally the electrons. So they're not being stolen from one to the other, they're both being used equally. This is a very, very strong type of bond. All right, here's a representation of both of those types of bonds. M for metal, NM for nonmetal. In this case here, this electron is being stolen to go over here, which makes this more stable, makes that more stable. But by losing an electron, the metal becomes positive, the nonmetal becomes negative, because it gained that electron. That's an ionic bond, a bond between two ions. For sharing electrons between two nonmetals, in order for these to become more stable, the outermost shell of electrons needs to have 8. That's why it's called the octet rule. You want to get as close to 8 as possible. So in order for that to happen, both of these need to gain 1, because they have 7. 1, 2, 3, 4, 5, 6, 7. Same thing over here. 2, 4, 6, 7. For them to become more stable, they need to share an electron. So by doing so, they both have 8. So they're not being stolen from one to the other, they're both being shared equally. That's a covalent bond. That's a very, very strong bond. All right, first we'll talk about positively charged ions. This is where metals actually lose electrons. All right, like we mentioned before, in an ionic bond, ions are going to be formed when an atom will either lose or gain a valence electron. And these will have very low ionization energies. They want to become more stable as easily as possible, so the energy needed to form the ion tends to be fairly low. Some elements are going to be much more likely to gain some, become more stable, and some elements will be much more likely to lose an electron and become more stable. And you can tell which one an element will do based on where they are on the periodic table. And the whole point is to become as stable as possible, and for most elements that is getting to the number 8, because that's what you have in the noble gases, the inert gases, because those are incredibly stable. And all these traits here are characteristic of the metals, the elements in group number 1, and also group number 2, and group number 13. Okay, negatively charged ions, these are where nonmetals gain electrons, because you're gaining something that's more negative. These traits will be true for nonmetals and the elements in group number 15, 16, and 17. Because you're gaining an electron, the energy that's going to be needed to form the ion tends to be higher, because it takes more energy to steal something away and gain an electron than it would be to lose it. Now these elements in these groups will gain 1 or more electrons in an effort to become much more stable. And of course the goal is, just like on the previous slide, positively charged ions, to become more or closer to the group of 8 in the outermost shell for electrons, because that represents a noble gas, which are very, very stable. Okay, like was mentioned before, based on the group number of where an element is on the periodic table, you'll be able to tell right away what charge an element will have as an ion, just based on where it's placed. See, for example, the elements in group number 1, or 1A, lithium, sodium, potassium, rubidium, cesium, they're in group 1A. That means they have one electron in the outermost shell. And again, the key thing for the majority of this chapter is the octet rule, number 8. So they only have one. It is much, much easier for these elements to lose 1 than to gain 7. So these are going to be very, very eager to lose that 1 in the outermost shell. So when they do so, by losing 1 electron, they become a positively charged ion. And sometimes you may see this as written as +1. You don't have to write the 1, it's understood. Just like in math, x is the same thing as 1x. You don't have to write the 1. Right, moving on to the next column, 2, or 2A. They have 2 electrons in the outermost shell. Of course, the goal is to get to 8, or as stable as possible. It is much easier for them to lose the 2 outermost ones than to gain 6. Because when they lose those 2, they become much more stable. The next lowest shell is already full. And that's what all elements want to do. They want to get their outermost valence shell of electrons to be completely full as much as possible. All right, so for those elements that are in column 2, or group 2, magnesium, calcium, strontium, and barium, when they lose their 2 outermost electrons, they become positively charged ions, but their charge is now +2, because they have lost 2. For every electron that you gain or lose, the charge will be changed by 1. So they have lost 2, so they are now positively charged 2. And same pattern for number 3, or group 3, aluminum. They have 3 electrons in the outermost shell. Much easier to lose those 3 than to find and gain 5 more. So when they lose 3 electrons, they become an ion with a charge of +3. Now as you get to the other end of the periodic table, this process switches the other way. For 5A, I say nitrogen and phosphorus. They have 5 electrons in their outermost shell. It is much easier for them to gain 3 than to lose their 5 in order to become more stable. So as they gain 3 electrons, they become negatively charged by 3. So their charge is 3 minus. So for group number 16, or 6A, oxygen and sulfur, they have 6 in their outermost shell. So much easier for that column to gain 2 than to lose 6. So the elements in this column, as they gain 2 electrons, will have a charge of -2, or 2 minus. And then the halogens, 7A, or group 17, they have 7. Much easier to find 1 more than to lose the 7 that they have. So they will gain 1 electron. As they do so, they form a negatively charged ion, and their charge will be -1. And then the noble gases, very, very end, already have their outermost shell filled at the number 8. So they are very stable. They don't lose or gain electrons because there's no point for them to gain or lose electrons. They're already stable like they are. So neon, argon, krypton, xenon, that whole column is fairly inert, fairly stable. So again, just by where an element is on the periodic table, you can tell what its charge would be as an ion. All right, next we'll talk about properties of ionic compounds. Like the name implies, ionic compounds are compounds made of ions, so they're going to have positive and negative ions. The bonds that form them or hold them together will be ionic bonds. Remember, opposites will attract. So the positively charged ion will be attracted by the negatively charged ion. These kind of compounds also have very high melting points, and they're going to be solid at room temperature. So a common example of an ionic compound is sodium chloride, more commonly known as the simple table salt. When you have these two together, sodium is much more likely to lose an electron, and chlorine is much more likely to gain the electron. So when they hook up together, the way you'd write sodium ion Na+, because it's +1, or chloride Cl-. So these are 2 ions being formed, and that's how you get sodium chloride, or common table salt. Now we'll move on to the formulas for compounds. In a chemical formula, the symbols and the subscripts are written in the lowest whole number ratio of the atoms or the ions. The sum of the charges needs to be 0. The number of positive charges will equal the total number of negative charges, so they can balance out. So for the example we just talked about sodium chloride. The sodium will lose that one outermost electron to fill out chlorine's outermost shell to make that full. So by doing so, the sodium side of this compound has a +1 charge, the chloride side has a -1 charge, so those added together balance out for a net charge of 0. So sodium chloride is a neutral compound. Now we'll move on to naming and writing ionic compounds. Iodized salt contains potassium iodide, written as Ki. This is used to help prevent iodine deficiency. And the learning goal for this portion of Chapter 6, given the formula of an ionic compound, be able to write the correct name and also give the name of an ionic compound and also to write the correct formula. All right, when naming an ionic compound, there are certain rules and certain protocols that you have to follow in order to name them correctly. So for an ionic compound, the name of the metal is always written first and is the same name as the element. The name of the nonmetal part of the compound is the first syllable of that nonmetal's name and the ending "ide." And there is a space between those two words, the nonmetal and the metal part. And we'll go over some examples here. Alright, this table has some very common examples. One we just talked about with the picture of the salt, Ki. K is the metal, that's potassium. The nonmetal ion would be, the element would be iodine, but when you're forming an ionic compound, it becomes iodide. So these two together, when you're reading this as a compound, potassium iodide. So not iodine, I-N-E, but iodide, I-D-E. Magnesium and bromine together. So when you are saying their name as a compound, magnesium, because that's the metal, that comes first, and then bromide, Al2O3. The metal part would be aluminum, nonmetal would be oxygen, but you're dropping the ending of the word oxygen and adding the ending "ide." This is the same process for all ionic compounds. Metal first, nonmetal second, and the ending will always be "ide," I-D-E. A step-by-step process on how to name ionic compounds. You need to identify the cation and anion. The cation is the positively charged element, so that'd be the metal. So identify which is the metal, which is the nonmetal, or which is positive, which is negative. I name the cation or the metal by the element's name, and then for the anion or the negatively charged portion of the compound, you drop its ending and add the suffix "ide," ide. And form those together. The metal goes first, or the positive part goes first, and the negative or the nonmetal part goes second. Here's another example. If you're given this formula, K2O, so step 1, identify which is the cation or the anion, or the metal and nonmetal. So the cation is going to be the positively charged portion, while potassium is the metal. Where this lies in the periodic table is in group 1, so that just by knowing where it's placed in the table will tell you that will be an ion with a positive charge, so that part of the name will come first. So oxygen will be the negative part, so that would be the second part of the name. Alright, because we're forming an ionic compound, the name would not be oxygen. You would drop the ending of oxygen and turn it into oxide. And then step 4, we put all that stuff together. Middle part goes first, potassium, then oxide. Now the transition metals, except for zinc and cadmium and silver, form 2 or more positive ions, so 2 or more cations. Help to distinguish between those is to use a Roman numeral as equal to the ion charge that's in place in parentheses just after the metal's name. So for example, copper can either have a charge of +2 or just +1. So in order to use it correctly or name it correctly, in this example, copper with a charge of +2, you'd write the word copper and then the Roman numeral 2 right after that word. Copper with a charge of this +1, you'd write the word copper and then the Roman numeral 1 just after the name. Iron is another example. It could either be +2 or +3. So iron 2, iron 3. Lead can be a +2 or +4. So lead, Roman numeral 2, and then lead, Roman numeral 4. And the last pair of examples, chromium can be 2 or 3 positive. So chromium 2, chromium 3. Now knowing how to use these correctly will help you determine how to write a formula correctly. Because if you don't know what the correct charge is for these transition metals, you won't be able to name or write a correct formula. Alright, here's a quick summary of the last few slides. So all the elements in group 1, or 1A, will form an ion with a positive 1 charge because they lose that 1 electron. Group 2, or 2A, will lose 2, so they are positively charged 2, so 2 plus. Going over here, group 13, or 3A, these will have a charge of plus 3. 15, or 5A, will have a charge of negative 3, because they are more likely to gain 3 than lose their 5. Group 16, or 6A, so their charges as ions will be negative 2. 17, or 7A, they're only going to gain 1. Their charges are negative 1. And the transition metals, examples we talked about here, lead, cobalt, nickel, copper, can either be plus 1, plus 2. Nickel can be plus 2 or plus 3. Iron, 2 or 3. It just depends. That's why you must use the Roman numeral after the name to identify which form of the ion that you're talking about. So again, another step-by-step flowchart to naming an ionic compound with a variable charge with the metal. Step 1 is just the same. Determine what is the positively charged, or the cation, what is the negatively charged, or the anion. Name the cation by its element's name, and then use the Roman numeral after that name for clarification. Name the anion, dropping the ending of its word, adding the suffix IDE. And step 4, putting all that together. Alright, here's an example of these steps broken down. Let's say you're given the formula FeCl2. Same thing here, FeCl2. And that 2 should be a subscript. You have two elements. You have Fe, which is iron, or chlorine, which would be Cl. Now chlorine, because it's in group number 7A, or 17, will gain 1 electron and become more stable. So that is the negatively charged part of this compound. So this part is going to be negative, and of course this part has to be positive. The positively charged cation would be the iron portion, and the negatively charged anion of the compound would be the chlorine. Okay. In the given formula, you have 2 chlorine ions, so that means that portion of the compound will have a negative 2 charge. Each chlorine has a negative 1 charge, and you have 2 of them, indicated by this number. In order for this compound to be neutral, there must be 2 positively charged iron ions to balance it out. 2 positives here for iron will balance out the 2 negatives of the chlorine. So that must mean that you're using iron number 2. And because this is a ionic compound, you would not use chlorine as a name, you would use chloride as a name. So putting all that information together, the formal name for this compound, FeCl2, would be iron 2 chloride. If you leave that portion off, the 2 in parentheses, that makes the name incorrect. You must have the Roman numeral after the name iron to make this specific enough to be correct. Alright, now we'll move on to polyatomic ions. Now poly means more than one, so these are going to be ions that have more than one atom. As an example that's given here first, sodium chlorite, NaClO2. This is used in bleaching of pulp from wood, and also used to recycle cardboard. So for this next section of this chapter, we'll talk about how to write the formulas for polyatomic ions and how to name formulas if you are given them. Here are some common examples of polyatomic ions and their names and their formulas. The nonmetal hydrogen, its ion would be hydroxide, or OH-. For nitrogen, you can have multiple forms of an ion. NH4 plus would be ammonium, NO3 minus, nitrate, NO2 minus, nitrite. And there is a difference between these endings. It's very easy to get those confused, so make sure that you are being very careful when it comes to these names. Some other common examples of the carbon. An ion could be CO3 with a charge of 2 minus, carbonate, HCO3 negative, or bicarbonate, or hydrogen carbonate, CN with a negative 1 charge, at cyanide. So these are some very common polyatomic ions in this chart, both with its nonmetal, ion formula, and then also the correct name. Now names of most of your common polyatomic ions will end in the suffix ate, 8. Like sulfate, phosphate, nitrate. And here are their formulas. So SO4 with a charge of 2 minus is sulfate. This has to be the number 4, and the charge has to be negative 2 to be sulfate. If it's anything different, it's a different compound with a different name. Phosphate, PO4 with a charge of negative 3, and nitrate, NO3 with a negative 1 charge. If a related ion has one less oxygen, the ending of the name changes. So instead of being 8, it becomes ite, I-T-E. So instead of being up here, SO4 with a charge of 2 minus, if you lose one of these, SO3 with a charge of 2 minus, that is sulfite, not sulfate. PO3 with a charge of negative 3, phosphite. Up here it's PO4 with a charge of negative 3. NO2 with a negative 1 charge, nitrite. All because you're losing one oxygen. And there are some exceptions to this rule, just like in everything else. The compound CN with a charge of 1, cyanide, and OH charge of negative 1, hydroxide. And lastly, when you add a hydrogen ion, H+, to the polyatomic ion, you add a positive 1 to its overall charge based on how else the other bonds are formed. Alright, halogens will form 4 polyatomic ions with oxygen, and each of those has a charge of negative 1. So for example, ClO4 with a charge of negative 1, that compound is commonly called perchlorate. If you have ClO3 with a charge of negative 1, that's chlorate. ClO2 with negative 1 charge, chlorite, and ClO with a charge of negative 1, hypochlorite. So those are all examples of the halogen chlorine, the element chlorine, forming a polyatomic ion with oxygen. Depending on how many oxygens are there will determine the compound's name. Now writing the compound for a polyatomic ion follows the same process as a simple ionic compound. The charges have to equal 0. So for example, if you are combining the magnesium ion and the nitrate ion, magnesium as an ion has a charge of positive 2. The nitrate has a charge of negative 1. So in order for that to balance and equal a net charge of 0, you need to have 2 of this whole unit, because you have all this has a charge of negative 1. So getting 2 of those will give you a overall charge of negative 2. Those negative 2 charges plus the positive 2 for magnesium balance out. So you need to have 2 of this entire thing here to balance out the positive 2 for magnesium ion. And the way you would write that is this: magnesium, and then this whole unit, NO3, is nitrate, but you want 2 of those. So just this has a negative 1 charge, but you have 2 of those to get negative 2, adding that to the positive 2, net charge of 0. But you must have parentheses around that ion and the subscript on how many that you need of that ion. So we're not talking about just nitrogen or just oxygen. All of this together is nitrate. Alright, some steps when you're naming an ionic compound with polyatomic ions. First, you need to find the positive ion, usually a metal, and then write the name of the polyatomic ion second. So here are some common examples. Na2SO4. The sodium will be the positively charged ion, so that'd be the first part of the name, so it's going to be sodium. SO4, that whole unit that's in this box, is sulfate. So this compound, sodium sulfate. FePO4, iron. Iron will be the positive part of this. The first part of the name would be iron. Phosphate, PO4, it's all of that, not just phosphorus, not just oxygen, but that whole unit together is phosphate. In order for these charges to be equal, you need to have iron with the Roman numeral 3 after it, because PO4, phosphate, has a negative 3 charge. So this whole thing in the box has negative 3. So in order for that to balance, you need to have 3 positive charges. So iron 3. And again, if that number isn't there, then the answer is wrong. If you have iron 2, it's wrong. This is the only way to correctly write this formula's name. Iron 3 phosphate. The last one, Al2, and then CO3 in parentheses with the subscript 3. Aluminum would be the metal part of the name, the positively charged ion, so Al2. And the CO3 is carbonate. You need to have 3 of these to balance out with the positive charges of aluminum. So aluminum carbonate. Right, now we'll talk a little bit more about covalent bonds. Now, again, this is formed when 2 or more nonmetals share electrons equally to form a very strong type of bond, covalent bond. And it's done so by sharing the electrons in the outermost shell, the valence electrons. There has to be at least 2 to form a compound. There's no limit on how many that can be in a compound, but you must have at least 2 to form any type of compound. Now, when naming a molecular compound, the first nonmetal in the formula is named by its element's name. Then the second nonmetal is named by using the first syllable of that name and then the ending IDE. A subscript is used, then that prefix is used in front of its name. So here's some common examples. Mono will mean 1, di means 2, tri means 3, tetra 4, penta 5, 6 hexa, 7 hepta, 8 octa, 9 nona, and 10 deca. And it's this process that is used for any type of molecular compound, for any type of compound between two or more nonmetals. Some common examples: CO2. The first nonmetal in this example would be carbon. So the first part of the name is carbon. This is oxygen, but because we're forming a compound, we drop off the ending of oxygen, turn it into oxide. And because the number 2 is here, you add di in front of that. So carbon dioxide. Carbon with 2 oxygens there. CO, carbon monoxide, because there's only 1. When there's no subscript, you just assume that the number 1 is there. You don't have to write 1 all the time. See, whenever you have vowels that are right next to each other, like O and O or A and O, you just drop the first vowel because it would just look really weird and sound really weird. So look for here, CO, you would not have mono, M-O-N-O, and then oxide, O-X-I-D-E, because you have 2 O's right by one another. Same thing here, NO, nitrogen monoxide. You would not have 2 O's right here. So if you have 2 O's together, you drop the first one. If you have an A and an O together, you drop the first one. Right, here's some common formulas and names for molecular compounds. CS2, carbon, that's the first nonmetal in the name. Carbon disulfide, because there's 2. CO2, we just talked about, carbon dioxide. NO, nitrogen oxide. N2O, dinitrogen oxide, there are 2 nitrogens. SO2, sulfur dioxide. SO3, sulfur trioxide, because there are 3 oxygens. And SF6, sulfur hexafluoride. Hexa means 6. Think of hexa like a hexagon, has 6 different sides. Alright, now we'll move on to double and triple bonds. Everything we talked about so far has just been regular single bonds. Now a double bond will occur when atoms between 2 pairs of electrons. And this is usually formed when there aren't enough electrons to complete the outermost shell. So sometimes these bonds will double up in order to fulfill that outermost shell to make it more stable. And with a triple bond, when atoms share 3 pairs of electrons. And just like with the double bond, usually formed to help make the atom much more stable, and when there aren't enough electrons to go around to make the outermost shell full. Alright, next we'll talk about the polarity of bonds. Now the difference in electronegativity of the atoms that are bonding together can help you predict the polarity of that bond. So for example, that's given here. Hydrogen. Hydrogen, when it naturally occurs, what's called a diatomic element that has 2 atoms, is always going to be represented by H2, because there are 2 of them here. So in this example, the electrons are shared equally by both of these atoms. So when they're shared equally, the bond will be nonpolar. In this example, hydrogen chloride, but there is a difference in the electronegativity between hydrogen and chloride. So when you look at this compound, the chloride side will be more negatively charged than the hydrogen side, just by comparing the parts of that compound. So not the overall charge, but the region of chlorine is more negative. In the region or the area of the hydrogen would be more positive. Because these electrons are not shared equally, there's going to be a difference of electronegativity. So that bond will be considered to be polar, because there's a difference there. Alright, now we'll talk about some different types of covalent bonds. A nonpolar covalent bond. This will occur between nonmetals and is either going to be equal or very, very close to equaling the sharing of electrons. So there's a very, very small difference in electronegativity. So here are some common examples. Nitrogen is another example of being a diatomic atom. There are 2 nitrogens whenever it's found naturally. It's like with hydrogen. So there's going to be no difference in electronegativity. That's nonpolar covalent. Chlorine and bromide, very, very small difference. That's also going to be nonpolar covalent. And hydrogen and silicon, a very, very small difference also. So because that difference of electronegativity is either very, very small or almost 0, that's considered to be a nonpolar covalent. A different type would be a polar covalent. These occur between nonmetal atoms. In this type, there's an unequal sharing of electrons. So in this example, because you have unequal sharing, there's going to be a moderate difference in electronegativity. So for oxygen and chlorine, only 0.5. That's going to be polar covalent. Chlorine and carbon, 0.5. Oxygen and sulfur, 1. So these are all more than these values. These are very, very small, no more than 0.3 or so. When the difference gets a little bit higher, that's when it becomes a polar covalent bond. Now that polar covalent bond can become more polar as those differences get higher and higher and higher. Now the separation of these charges in a polar bond is called a dipole. Di meaning two, and pole meaning polar ends. So think of this as almost like a bar magnet, where you have two separate ends with totally different charges. So like for a bar magnet, you have a north and a south. So for these kinds of bonds, one part of the compound would be much more negatively charged, the other end would be much more positively charged. And you can indicate this by using some Greek letters and also by using some arrows. Now the lowercase Greek letter delta is used to write or to indicate positive, negative. This example here, the bond between carbon and oxygen. When you have this compound, the oxygen side is more negative compared to the carbon side, which is more positive. Delta with the plus indicate positive, delta with the minus indicate negative. You can also draw these arrows here. The arrow will point to the more negative end of the dipole. Same thing with nitrogen and oxygen. When these two form a bond together, the oxygen side will be much more negative compared to the nitrogen side. So positive for here, negative for here. And the arrow going toward the O. And when chlorine and fluorine get together, fluorine side is going to be much more negative, and the chlorine side will be much more positive. The arrow going toward the negative end of the dipole or the fluorine. All right, talk a little bit more about the traits of a ionic bond. These will occur between metals and nonmetals. These are formed when you have a result of an electron transfer, either gaining an electron or losing an electron. And these bonds have a very high electronegativity, 1.8 or higher. Some common examples: chlorine and potassium. That difference is going to be 2.2, so that forms an ionic bond. Nitrogen and sodium, 2.1 in difference, ionic. So a big indicator of if a bond is an ionic bond is the high difference in the electronegativity between the two elements. Alright, next section of chapter number 6, the attractive forces in compounds. So the shape of a protein can be twisted and bent based on how amino acids and various other side chains interact with one another and how they're attracted to one another. So this will help a protein form a three-dimensional shape. And for proteins, its shape helps to determine its function. Learning goal for this portion of chapter 6, describe the attractive forces between ions, nonpolar covalent molecules, and also polar covalent molecules. Alright, for covalent compounds and polar molecules, these have attractive forces called dipole-dipole attractions, because you have attractions between ions that are dipoles. You also have very strong dipole attractions called hydrogen bonds between hydrogen ions that are bonded to either fluorine or oxygen or nitrogen. The hydrogen bonds are the strongest force between molecules and play a very major role in the shaping of DNA. DNA has a very helical or a spiral staircase shape to it, and the reason why you get that shape is due to hydrogen bonding between amino acids and the side chains within the DNA. So here's some examples: hydrogen chloride, nitrogen chloride. The bond between the hydrogen here and the chloride here is a dipole-dipole attraction because you have an attraction between two dipoles. Positive end here is attracted to the negative end here, because remember, opposite charges attract. That's how they're able to combine together. For here, the hydrogen end here, and then the nitrogen end here. The positive part of the dipole attracted to the negative end of the dipole here. That's a hydrogen bond. Alright, dispersion forces. These will be very weak attractions between nonpolar molecules, and these are caused by what are called temporary dipoles that will develop when molecules bump into one another. But they don't last that long, so that's why they're considered to be temporary. And these forces are going to be weak, but it's also what makes it possible for nonpolar molecules to form solids and liquids. So with this example here, this nucleus and electrons floating around here in this atom are equally distributed. One on that side, one on that side, one on that side. Over here for this atom, they are not equally distributed. The nucleus at different locations, the electrons aren't equally distributed. Or if these two were to bump into one another, You have the negatively charged end over here being attracted to the positive charge end over here. This is a temporary dipole, so a temporary weak attraction. Alright, next we'll move on to melting points and attractive forces. The melting point of a compound is related to the overall strength of the attractive forces between the molecules of the compounds. The higher the melting point, the more energy, the more heat would be needed to break those apart to melt that compound. And these are going to be lower due to weak forces, such as dispersion forces. So if the attractive forces between the atoms are relatively weak, it won't take that much to melt that sample, so that melting point will be fairly low. And melting points will be higher if you'll have the stronger types of attractive forces, such as hydrogen bonding. The highest melting points are going to be found in ionic compounds due to the strong attractive forces between the ions within that compound. Here are some common examples. First two here, ionic bonds. Magnesium fluoride, melting point 1,248 degrees Celsius. Sodium chloride, basic table salt, 801 degrees Celsius. A compound has a hydrogen bond like water. Melting point is 0 Celsius. And NH3, negative 78 Celsius. So we're getting a lower and lower melting point. Compounds that have a dipole-dipole attraction. Hydrogen bromide, negative 89 degrees Celsius. Hydrogen chloride, negative 115 Celsius. And some examples where the attractive force is only a dispersion force. Chlorine atom, Cl2, negative 101. And fluorine, just F2, negative 220 degrees Celsius. Here's a chart that describes the weakest up to the strongest types of bonding between atoms and between ions. So we'll start with the weakest one here at the bottom. Dispersion forces. These are going to be very temporary, very weak. So the next strongest would be dipole-dipole attractions. We have attractions between nonmetals. Next strongest would be hydrogen bond. So those are the attractive forces between molecules. The next two, or the top two, will be between atoms or between ions. Covalent, we have a bond between two nonmetals. And then ionic, we have two or more ions that are formed. Thank you for watching our newest video on our crash course in chemistry. We'll have new videos in this lecture series every Monday and every Friday of each week. So stay tuned for our next video in a few days. And don't forget to subscribe to this channel so you can be notified of when our new videos are posted each week.